Hello and welcome to Electronics 4. This is a recap episode, so I'm going to be going through pretty much everything I've gone through in episodes 1 to 3. I've written out a fair amount here, so let's go through it. So the beginning is just a sort of general statement. Often in these sort of things you do sort of say something which is a bit more general, a bit more complicated. So all electrical phenomena derive from the movement of electrons. So electrons exert an influence on the electrical field around them in 3D. It's a force that acts at a distance. So it's all dependent on electrons and the field, which of course we'll be speaking about later, three-dimensional field, and they exert an influence on that. So then, of course, I moved to static electricity, and this was in some ways like a background sort of thing. Mainly to see how to see what led to the discovery of electrons and things like that. So after being rubbed together, silk and glass stick together. So it was basically an attraction after they're rubbed together. Same for the head and balloon, and wax wool cloth, and obviously. It's kind of it's quite a strange phenomenon, I guess, because you would think like if you rub your head in the balloon and you put a balloon on the wall, you'd think that gravity is going to just make it fall down straight away, but it doesn't. So from there, it's quite easy to see this is something quite strong we're dealing with. If it is able to withstand the whole gravity of the whole Earth. So yeah. And also it was noticed that even when separated, these things had an attractive force. So force that acted at a distance. So even when you're not actually, you're not like just connected to each other. There's something going on in between the objects. Okay, and as I said, take one piece of wax rubbed against one piece of wool cloth. Take a separate piece of wax, rub against a separate piece of wool cloth. And you see that the pieces of silk are going to repel each other. And the piece of wool cloth also going to repel each other. So and obviously this is going to be about the fact that you've got the protons are repelling each other, the electrons are repelling each other, and this sort of stuff. And about how obviously the same signs will repel and opposite signs will attract. So and I don't know quite what this next bit is. I mean, obviously I didn't do it quite like this one I actually originally did it, but I just wanted to make it as clear as possible, even in this paragraph, to try and make it very, very clear. I mean, you possibly could use the same material. So I sort of put it in different categories. Just to sort of clarify that, that any material demonstrate properties of attraction or repulsion will be attracted to glass and repelled by wax. So attracted to what's in B there and repelled by what's in A, or attracted to wax and repelled by glass. So so you can see that they're obviously taking on different signs. But that's not what was believed at the time. So I don't want to get ahead of myself. Really, it's not the best thing to do. But even so, it's good to see it, because I might not explain it later. So next, there was an invisible fluid transfer, with two fluids being transferred over to create the effect, so known as charge. So I sort of thought, there's actually these two fluids going over, and they're both creating it. And it's sort of like some sort of charge, and you can see how it could be seen as a charged effect. Possibly, I mean, maybe probably, I guess it must have come from like charged situation or something like that, and which is where there seems to be an atmosphere. Maybe it's that sort of feeling. Anyway. So eventually they thought, it's not actually two fluids, it's only one fluid. But the two charges it's just one thing. It's one fluid, but it's excess or deficiency of that one fluid. So that was the sort of next breakthrough, if you like. So if we go to wax and wool, wax and wool seems to pop up a lot. it seems to be quite a common thing, and I suppose they're quite common items as well. So you might not have much silk around, I suppose. But anyway, so wax and wool. The wool removed the fluid from the wax, causing excess on the wool, and the attractive force seen as the fluid attempted to regain balance. So at this point, anyway, well, obviously, I'm going to be speaking about this later as well. This is not actually the case, so I should point that out. But in a sense, but this is how the nomenclature. I didn't want to say that word. Nomenclature of the whole thing was decided, and why electrons, not perhaps as you might think. Not that I might think anyway. It's just one of those conventions which is a certain way. But anyway, so the idea was that the wool removed the fluid from the wax. So you rub them together. The wool is taking the fluid away, causing excess on the wool. So there's too much on the wool. There's less on the wax, and so the attractive force is some sort of attempt to regain sort of balance or equilibrium, or just a level playing field. So yeah, so the wax lost fluid, so it became negative, and the wool gained fluid, so it became positive. So because of the way that was thought of, it made sense to say that this wax is has got less fluid. Obviously, at the time, they probably weren't thinking about. I don't know. Maybe it was it's one of those things that they probably, if you measured the weight of it, it probably wouldn't. You wouldn't have been able to tell anything. But it was sort of seen more, I don't know, more ethereal or something like that. So it became negative, and the wool gained fluid, so it became positive. So that's basically what they're thinking. All right, then it started to get into this. Some of this stuff I didn't actually put in the original episodes, but I wanted just to put a little bit extra. This particular bit I didn't put in. So anyway, there's this thing called a torsion balance. And it basically found out that, like many other things in classical mechanics, inverse square law was basically inverse square law always is all over the place in classical mechanics. Yeah, but obviously it's just electronics, so I'm not going to talk about its applications to other subjects. But anyway, so yeah, so you had this ball with a known charge hanging from a silk thread, and another similarly charged ball. So you knew the charge already. It was calculated before, probably by some. Just push these at a certain force, maybe, or that was probably you could probably do that. But anyway, you got another similarly charged ball brought nearby, and the rotation of the thread, you measured that angle, and then if you did like multiple different charges, and different separation distances between the two balls, the force law was made, right? All right, and then obviously at this stage, once you've got this equation, I suppose it would make sense to calculate for 2-point objects, because that is it's just the best way to do it, really. It's how using point objects, you can you ideally want to get this universal elementary sort of thing going on. So anyway, so you get 2-point objects. So there's no surface area. It's just hypothetical for the purposes of calculation. So if we just say the charge to 1 coulomb placed 1 meter apart, generate force 9,000 million newtons. So 9 times 10 to the 9. Okay. And obviously it's attractive or repellent depending on the type of charge. So that was a way to to quantify what was in newtons this charge, even though as we'll find we're going to be using a lot of different units, not newtons. Okay, so later on, this is because obviously this stuff was happening sort of 18th century start. Later on, probably about 100 years later or something, it was discovered the fluid was not fluid at all, but in fact composed of tiny bits of matter known as electrons. And there's basically there's 3 fundamental particles comprising most atoms. They're protons, neutrons, electrons. All atoms have got to have protons, and electrons, but neutrons not necessarily required. And at this stage, this is actually when I drew the picture of it. But yeah, so basically, but I didn't feel I really needed to draw the picture. I probably didn't even mention shells, but the point is that yeah, there's basically the 6 protons and 6 neutrons all tightly bound in the middle, and that's because of, as I mentioned in a minute, the strong nuclear force. And then you've got the two outside in the nearest shell, because obviously, you know, that's all it can take, that immediate shell there. It's got 2 there, and then you've got 4 in the next nearest shell there. So obviously, it's not full, not empty, really. Yeah, large, and so there's large between both central cluster and nearest shell next to it. So basically, the point I was trying to make here in general was large amount of empty space. Yeah, because it's hard to exactly say, but in reality, yeah, that is what atoms. You know, it's well known that's what atoms look like. That you just have the loads of the very tightly packed cluster of the protons and the neutrons in the middle, and then the electrons are very, very free. Dislodging them is not a big deal compared to huge the effort it takes to dislodge protons and neutrons from the central cluster. And protons are what decide the elemental identity. So if you did remove 3 protons from an atom of lead, you can make an atom of gold. And obviously it's very, very difficult to do, that sort of stuff. If you've got more neutrons there, it's still going to be the same element, but there's going to be different nuclear properties. There might be radioactivity, for example. And like I've just mentioned, electrons have significantly more freedom to move around than either protons or neutrons. So just dislodge them, and it's very important fact, of course, with all the stuff that I'll be talking about in the chemistry, I guess. But basically, like, they can be knocked out of their respective positions or leave the atom entirely using far less energy than it would take to dislodge particles in the nucleus. Okay, so electrons and protons attach to one another over a distance. So this is the force at a distance. So basically, this force at distance is obviously is actually the electrons and the protons being attracted to each other. And obviously there's the process is involving the electrons being moved away from the original atoms and residing around the atoms of another object. So like I was saying earlier, the rats lost the fluid and so it became negative, and the wall gained fluid so it became positive. Okay, but it turns out the converse is actually true. The electrons in the wall transfer to the wax in the rubbing process. So you could paraphrase that. So the wall had lost fluid, so you couldn't do that. If you did paraphrase it, you'd have to change it. So let's not paraphrase it. All right. But basically, the point is that the idea that the wax had lost the fluid and became negative, and the wall had gained the fluid, was actually, the converse was actually true. So in effect, what actually happened is that this idea was actually maintained because the wax had gained something, gained the electrons from the wall. It was a surplus of electrons, but because it was originally called, because it thought it had lost fluid and it was originally named negatively, this meant that a surplus was actually negative. So this is actually probably the most important point of this whole section, because to understand that a surplus is negatively charged, and the deficiency of electrons is positively charged. So when we have and even though I suppose if you learn it like that, it's not that counterintuitive, but it is a little bit counterintuitive in terms of you would think that a surplus would be positive, but it's actually the opposite way. So wall's got deficiency, so it's positive. Wax a surplus, so it's negative. So that's all of it. So you've got the electrons, you've got the piece of wall there. Piece of wall's got all the electrons on it, and then once you rub it with the wax, the electrons jump from the wall over to the wax. The wall is left with a deficiency, so the wall is positive, and the wax has got a surplus, so it's negative. Okay, so so electrons repel each other at a distance, as do protons. So this is why the we've got the silk. Silk are gonna repel each other, stuff like that. It's because well, we've got the wall. If you've got the wall, so it's positive. So that's going to so it's going to be protons, I guess. repelling each other there, and wax is going to be like the electrons repelling each other. That works? It might work like that. Well, I'm not talking about that anyway. So electrons repel each other, it's protons. Protons bind together in the nucleus because of the strong nuclear force. The force is only effective over very short distances. Okay, so if okay, so yeah, just they did get cut off, but so the early idea was maintained. So surplus of electrons said to be negatively charged, deficiency of electrons said to be positively charged. So we've all got deficiency, so it's positive, and wax a surplus, so it is negative. So yeah, so you could almost say like it's like the deficiency. So the deficiency is positive, and wax surplus is negative. Yeah, and that's because of the earlier belief around the fluid structure. Okay, so electrons repel each other as do protons. So the negative electrons are going to be repelling each other. The positive protons repelling each other. So negative repel. Positive repel. Protons bind together in the nucleus because of strong nuclear force. It's only effective over very short distances. The strong nuclear force. So yeah. So if electrons leave or extra electrons arrive, the atom's net charge will be imbalanced, leaving the atom charged as a whole. So yeah, so it's going to be yeah, the ion basically as a whole, causing it to interact with charged particles and other charged atoms in the vicinity. So yeah. So Coulomb is deficiency or excess of 6.25 times 10 to the 18 electron. It might be 6.24, but yeah. I think it's 6.25. Anyway, it's not going to make much difference at this stage. Yeah, and electron, there's a charge just minus 1.6 times 10 to the minus 19 coulombs. And electron is the smallest known carriage of electric charge, is therefore known as the elementary charge. I believe also every single electron in the universe is exactly the same. So imbalance of electrons is called static electricity. It has a name because the electrons tend to remain stationary after being moved from one insulator to another. So yeah, and that was something I didn't really talk about. I'm talking about insulators here. Obviously, we've got a very different story with conductors. But yeah, so yeah, so like I said, surplus is negative, deficiency is positive, and I also mentioned static electricity, high voltage and low current. So yeah, I think that's pretty much all I spoke about. I mean, I don't know. I don't think I spoke about much else really. But that was all I really wanted to talk about in this recap. Yeah, so static electricity. Yeah, I mean, it was really been about this whole section. You know, once you rub the items, the electrons are going to be stationary. There's not going to be further, development with the electrons. So yeah. But obviously, well, there would, but I suppose it would be if you rubbed it again. But yeah, if you just do it, but obviously, this is speaking more about sort of instance in time. But anyway, I'm going to leave it there. I believe I'm just going to wait a few seconds, and because of obviously the video gets cut off a bit early, so if it gets cut off at this point, it's like it doesn't matter so much, because I'm just it's just the end anyway. All right, thanks for watching.